Yeah, okay, so let us start. So in the last lecture, we saw how to calculate the delay of the inverter chain. So I hope my screen is visible to you and my voice is also audible.
Yes, sir.
Okay. Yeah, so now let us talk about how to design the combinational logic circuits using the same CMOS style. So we'll talk about the combinational logic circuit design in this portion of the course. So you see, a difference between a combinational and sequential logic could be that in a combinational logic, you will understand that the outputs, so they are function of present inputs only, right? So in a combinational logic circuit, the outputs are function of present inputs only. And however, in the sequential logic circuits, so you will find that output depends on present inputs also and the previous inputs also. So you will see that there is some sort of feedback coming from the output to the input again, right? So these are sequential circuits where you will find that the output of the circuit is dependent on, or it's a function of both present inputs and the previous inputs. Now, before understanding this combinational logic circuit style, let us also once again talk about this static CMOS circuit. So in fact, we have been so far discussing about only static CMOS circuits. So from the static CMOS inverter, the static complementary CMOS circuits can be arrived at when you have more than one input. So CMOS inverter, we had only just one input. So static complementary CMOS circuit can be implemented with more than one input. So one of the characteristic of this static CMOS circuit is that the output of the gate, right? So it is always connected to either VDD or VSS, right? So every point of time, at every point of time, you will see that the output of the gate is connected to either VDD or VSS. Yeah, so this is one of the properties, important properties of static CMOS circuit. Then the other property is that the output of the gate, so it assumes the value of the Boolean function which it is implementing, right? So all the time the output of the gate will have or will hold the value of the Boolean function implemented by the circuit. Okay? Now this is in contrast to the dynamic circuit clash. So in the dynamic circuit clash, the output is temporarily stored on some capacitor, capacitance. So here the output is always connected to either VDD or ground. But in dynamics, we have output which is stored, which is temporary outputs that is stored on some capacitor at the output. Now, since the output is stored on the capacitor, so it obviously means that this dynamic circuit needs some sort of refreshing. That is, some clock cycle or clock is required, which can refresh the value of the capacitor, because the output of the capacitor that will obviously discharge after some time. So it needs some sort of refreshing circuit. So a clock is a necessary thing. Some minimum clock period is a necessary condition, necessary requirement for dynamic logic circuit. Though dynamic logic circuits are obviously fast, they are faster than static, but then there are issues of noise and also power dissipation will be more, okay? And hence they are not much reliable compared to the static CMOS circuits. So we'll carry on our analysis on static complementary CMOS circuit in this section of the course. So for example, here you will find a static complementary CMOS circuit being implemented using a pull-up network which has PMOS only and a pull-down network which has NMOS only. And pull-up network and pull-down network, they both are dual of each other. So dual here means that suppose in a pull-down network NMOS are connected in series. So in a pull-up network, PMOSs will be connected in parallel. Okay, so that the output node is always connected to either VDD or VSS, right? So dual here means in pull-down network, if the MOSFETs are connected in series, so in pull-up network, the MOSFETs will be connected always in parallel. Now, if we talk about NMOS transistors in series and parallel, so what logic they implement? So let's say if A and B are applied at the gate, okay, and X is the input here. So we want to find out the output, right? So the output, that is Y, that could be equal to X if both A and B are high, right? So this means that it implements an AND gate. So if you have a series connection of NMOS transistors, so that behaves like an AND gate. So output will be equal to the input if both A and B both are true. Similarly, if the NMOSes are connected in parallel, so this implements actually a OR gate. So output will be equal to X if any of these two inputs, that is A or B, will be high. Right? And we also some time back discussed that NMOS transistors, they pass a strong 0 but a weak 1. So we are not going into this once again, but yes, we understand some time back we had discussed how it can pass a strong 0 and a weak 1. Then similarly, if we talk about PMOS switches in series and parallel, so we find that when PMOS are connected in series, for example this, so this implements a NOR gate, right? So PMOS in series represents a NOR gate, that is output would be only equal to X if A and B, that is A bar and B bar, so this is true, that is A plus B whole bar is true, right? So this represents a NOR gate. Similarly, PMOSes in parallel, so they represent a NAND gate. So the output again Y will be equal to X if A B this functionality is implemented, is A B whole bar, right? So this is true. So this represents a NAND gate, and some time back we had also discussed that PMOS transistors, they pass a strong 1 but a weak 0, similar to the NMOS transistors which pass a strong 0 but a weak 1. A PMOS can pass a strong 1 but a weak 0. Yes, so yeah. Now in a complementary CMOS logic style, the pull-up is dual of pull-down network. So that also can be shown using the De Morgan's theorem. Yeah, pull-up is dual of pull-down network. So the De Morgan's theorem, there are two things here to remember in De Morgan's theorem, that is A plus B whole bar is always A bar B bar, and AB whole bar is equal to A bar plus B bar. Yeah, so these two things are called De Morgan's theorems. Okay. Now you will also utilize these theorems maybe if you want to implement a complex logic circuit. So maybe you can restructure the logic circuit by utilizing the De Morgan's theorems, so that the number of transistors in final implementation are smallest as possible. Now the complementary gate that we would be implementing, that is CMOS logic style, is always a complementary logic style. That is, if you want to implement an AND gate, you will have to first of all implement an AND gate. You cannot implement an AND gate directly in CMOS logic style, since it's a complementary logic style. So it will always implement complement of any function. So if I want to implement an AND gate, I'll have to implement a NAND gate first and then invert the output of the NAND gate. So then only I can arrive at this AND gate. Similarly, if a NOR gate has to be implemented, so OR gate has to be implemented. So one has to first implement a NOR gate and then invert the output of the NOR gate to achieve a OR gate functionality. So this is an example of NAND gate being explained here using two NMOSes and two PMOS transistors. Okay. So we had discussed that A dot B, that is this implements a AND functionality. So here if you look at the table, so you can verify this. So when this is 0 0, A B are 0 0, so both are on, so output is high, right? So both are on, the output is fully charged. Similarly, when any of these two are on, so then also the output is charged to the VDD. And when both of them are on, A and B, both of them are on, that is this condition. So that means whatever is stored at the output node, so that will be discharged. Okay. So you'll have nothing on the output node, 0 at the output node. So 0 is being shown over here. So this represents a NAND gate. Now one thing you will notice here, that the the patterns of the inputs, that is, for example 0 1 1 0 and 0 0, these three patterns. Okay. So now the delay on all these patterns will be different, and especially in this case when both the MOSFETs are on, that is both the PMOSes are on. So when both the PMOSes are on, so that obviously means that both these will work to charge the output capacitance. So output capacitance can be charge quickly. So TPLH will be smaller in comparison to these two cases, where one of these transistors are only on. So that is one of the things one has to remember. That is, input pattern does can change the delay. So similarly, a NOR gate can be implemented again by using two. It's a two-input NOR gate, so two NMOSes and two PMOSes, and the truth table can again be verified here. So when any of the inputs, when any of the inputs are 1 or both are 1, the output is always 0. Okay. So when any of the input is 1, that is, NMOS is on. Both the MOSFETs can be on in this situation. NMOS can be on. So then also the output will be 0, and any of these two MOSFETs are on, then also the output will be 0. Okay. Now when both of the MOSFETs are on, PMOSes are on, then only the output will be high. So which is this condition. Okay. So that way one can implement a NOR gate. Again, you will notice here that when these two MOSFETs, that is both NMOSes are on, then the output node can be quickly discharged, okay, compared to only the case when one MOSFET is on. So that means delay in this case will be smallest, TPHL, that will be smallest in comparison to TPHL in these two cases. Okay. So this one has to remember. Now similarly, one can think about implementing any other logic, for example, and here in the previous case you will also notice that the pull-up, that is pull-up is dual of pull-down. So if you have a connection of parallel NMOSes in the pull-down network, so you have a series connection of the PMOSes in the pull-up network, right? So similarly, one can think of drawing the circuit of any other complex logic circuit. For example, let us say we want to implement output function which is equal to D plus A dot B plus C, right? D plus A dot B plus C and whole bar. So obviously D and this entire term, so these should be in parallel, right? So this D and A plus A dot B plus C and A dot B plus C, that is, these should be in series, because this implements a AND gate. So A dot B plus C here, right? So this is my pull down network. Now pull up will be the dual of this. So that means this portion, that is D and this A dot B plus C, they are appearing in parallel. So in the pull up network, these two will appear in series. That is this portion and this portion. That is this one. So these two should appear in series in the pull up network, right? And then similarly, A and B plus C. So A is in series with B and C. So in the pull-up network, A will be in parallel to B and C. Let us see how it looks like. So the pull-up network looks like this. Okay, it's a dual of pull-down network again. So A is now in parallel to B and C. B and C are now in series, and D is also in series with this entire, right? So that way one can implement any complex logic circuit, not just this. Now again, one has to remember here one important thing. And that important thing is that one has to minimize the number of transistors which are connected at the output. Okay. So this is my output node here. So one has to minimize the number of connections, that is in transistors which are present at the output. No, this is not the output. So output is here, this one. This is my output. So one has to minimize number of transistors. So some person can do is what can he do is that D can put up towards VDD, and this entire A, B plus C can be put down. So that case is not recommended, because in that case the output capacitance, so that will be too high, right? So I'm just drawing the PMOS, the pull-up network. So some person can do this thing, that is, he can bring the entire AB plus C, that is A plus BC, down towards the output node. So this is not recommended, because this will lead to higher capacitance at the output because of pull-up network, right? So we have now the, for example, here we had from the pull-up network, we had a contribution of just this D transistor at the output. But here, in this case, we have a contribution of two transistors, right? Two PMOSes. So similarly, that can be done for this pull-down network also. We don't want to bring all D, B, C near the output. Right? So one has to take care of this. That is, don't put more number of transistors at the output node, so that the load capacitance is kept small, so that TPLH and TPHL are small, so that the transistor or the circuit is fast. Now one can also think about drawing the layout of such cells. Okay, so for example, a 2-input NAND gates layout has been shown over here, and you will see here that for these two transistors, that is NMOSs, yeah, these two are NMOS. So for these two NMOSs, we are not utilizing a separate diffusion region, right? So one would say that since in an inverter, what we had done, we had simply connected one PMOS and one NMOS, right? So one would say, why not we draw another diffusion region for another transistor? That is, we have two transistors here, A and B. So why not draw separate diffusion region? So avoid drawing separate diffusion region. Try to draw the same diffusion region and try to locate all your transistors in the same diffusion region, for example, which is being done over here. So the entire diffusion region is being shared by these two transistors A and B, right? So this one is A here and this is transistor number B. So the diffusion regions have been shared here for both these two transistors. Okay, so for example, this point in NMOS here, right? So this can correspond to this region. The diffusion region is shared, that is source and drain. Okay, this is my drain of the upper one, source, and then again this is drain and the drain of this. So let's say this is transistor number 1 and this is 2. Okay. So the drains, source and drains of transistor number 1, 2 are shared. So they are shared here. We don't need a contact also here. But in this case, you will need a contact. So if I want to connect them, I'll need a contact. So I'll have a extra contact resistance. Okay. So the resistance of this region also goes up. But in this case, we don't have extra contact also, and the area is also small. The layout area will also be small. So try to use the same diffusion region for all the transistors. Okay. So in fact, there is a technique or method by which you can draw optimum layout. So we'll try to discuss that technique today in today's lecture. And that technique is called Euler method. Okay. So for Euler method, you will need to draw the Euler paths or Euler diagrams of such kind. Okay. So for example, somebody wants to draw the layout of this circuit, right? So this is C dot A plus B whole bar. Okay. So somebody wants to draw a layout of this circuit. So let us see how we will draw it, the layout of this circuit. Okay. So maybe let us take a screen. So let us say we want to draw C dot A plus B whole bar, right? So this is what we want to draw, the layout of the C dot A plus B whole bar. Yeah, sure. So this is what we want to draw. So if we try to draw the layout, so let us say that PMOS are lying on the top and NMOS are lying at the bottom. Okay. And let us say A, this is the gate of MOSFET number A, and this is B, and similarly this is C. Okay. Let's write the names. A, this is transistor number B, and let us say this is transistor number C. Now the placement of transistors, right? The placement of cells or maybe placement of transistors. So that is also very important. Okay. So in fact, placement and routing, I mean, how you will place the transistors on the layout or the chip and how you will route them. So these are one of the biggest challenges in digital IC design, in the layout design. Okay. So let us say we have A, B, C. They are sharing the diffusion regions. Okay. Now let us try to make connections. C dot A plus B whole bar. Okay. In fact, first of all, let us again try to draw the circuit. So the circuit was somewhat like this: C dot A plus B whole bar. So I have PMOS here. So these are my PMOS. Okay. And this is A, and this one is B, and this is C. And here I have VDD. Okay. Now this is my output node here. So this is NMOS C, and this is A, and this one is B maybe. And this is then ground. So this is the function y, which is equal to c dot a plus b whole bar, right? So let us try to draw the layout of this. And here we have output. Okay, so let us now try to make connections. Okay, so let us try to make connections in the NMOS here. So bottom we have NMOS. So we'll see that A, B, and C. So all are connected here. Yeah, A, B, and C, all are connected. Okay. So maybe that connection we can provide. Let's say B and C. Let's use this region for B and C. So B and C are connected here, and we want B and C to be connected. So we'll utilize the diffusion regions B and C over here, and let us select this for A. Okay? And let us make a connection over here. So this connection is established now. Okay? And then we also have to connect this A and B to the ground. Okay? So yeah, A and B have to be connected to the ground. So again, A and B, they are sharing a common region, diffusion region here. So I select this, and then maybe I'll say that here I have my ground line running. Similarly, I have a VDD line running up over here. Okay. So NMOS connections are completed. Only we need now to connect the output, that is C here, right? So this is C, and this is free here. So let us try to say that here my output will be present, Y. Okay. Now let us try to make the connections for PMOS. Okay. So PMOS, again you will locate this B and C. So B and C are connected to the output here, and B and C. So they are connected to the output. So let us identify this region B and C, which is common here, sharing a common region, and let us bring it to the output, right? And then you will see that A and C, they are commonly connected to VDD. Okay? And A and B, so they are also connected. So A and B, let us say A and B, this connection is for A and B. And for A and C, let us say that I will connect these two to VDD. So I'll bring it here, A, and this one for C, and I'll connect these two to the VDD. Right. So this is called actually placement and routing. That is how you will place the transistors, and then how you will route the connections to the drain and sources of these transistors. Right. So the layout of this transistor can be completed, right? In fact, a SIP circuit, right? So layout of this circuit can be drawn like this. Now, another way of drawing, someone would say that no, some other, style or some other layout can also exist for this. So let us try to draw another layout where I'll bring now C in between A and B. That is, I'll try to place MOSFET number C, that is for both PMOS and NMOS. I'll try to put in the center. So let us try to draw it here. Maybe in this small space we can draw. So this is my PMOS, and this is my NMOS here. And let us say this is A, this is B, or this is C now, and this is B, transistor number. Or in fact, this is not possible by using the same diffusion region. So I'll rub this. And this time I'll use a different diffusion region. Though the different diffusion region is not a optimum solution, okay? The diffusion regions have to be same as far as possible. But if you put C in the center, that is place your transistor number C here, then there is no other option other than to have a different diffusion region for transistor number B for the NMOS. Okay? Otherwise you cannot connect. Okay? Now one can make connections. So I'll make connections now. This will go to this point, and this will come to the ground, and from here one can take the output. Oh, no, not this way. Let us remove all this. Okay, so again let us try to draw. So from here I'll select the ground, and then transistor number C, A, and B. So all are connected here, and then from here I'll take output. So from here I'll take output Y, and then this will also be shared with C and B. So this is shared with C and B, and then A and B, they both are sharing. So A and B, they
Excuse me,
are,
sir.
yeah, please.
Hello.
Yeah,
So
please.
can you draw this in some other board? It is really not visible.
Okay.
Yeah.
So in fact, I'll show you here itself. Maybe I have it here. So I think this is visible now. So this is the second style where you brought, yeah, this is the second style where you brought C in between A and B. So I think the first one was clear. So first one had, A, B, C, all were sharing the same diffusion region. Yeah? So this is the diffusion region for NMOS and this is for PMOS. But here you will see that diffusion region is breaking over here. Right? So for B is utilizing a separate diffusion region and A and C are using a separate diffusion region here. Yeah? So this can be noticed from here also. So no need to go to the hand drawings. Okay.
Sir, here we take care of series and parallel correction or not, sir?
Yeah,
In
they will
these
be there
layout
always.
diagram.
Always series and parallel connections will always be considered. I mean, you have to connect these nodes. Yeah, all these nodes have to be connected in the layout. Okay? So either you share the diffusion regions or you don't share the diffusion regions. The transistors have to be connected in the same order. Yeah, this order will be maintained.
So, sir, we can find out from the layout diagram that what series connect, what elements are connected in series and what are connected in parallel through
Uh,
layout diagram.
yeah, from layout also you can find out what elements are connected in series and what elements are connected in parallel. So from layout also you can find out. That is okay, correct? But imagine that first of all we have circuit. Yeah, we don't try to extract circuits from the layout, but we try to draw the layouts from the circuits. Right. So we have circuit and we draw the layouts from the circuit. So
Okay.
now there are now two techniques. That means two different layouts you will
Sir,
see here. Yeah, please.
sir, what is the point of drawing C in between the A and B when you are saying that diffusion region should not be separate, it should share a common diffusion region?
Yeah, so that is what is required. I mean, that is what I was trying to say that this is not efficient style, okay? Because now the layout area is also more, and the extra contacts also are present in the diffusion regions of both the MOSFET C and B. So this is not more efficient. Style number one is more efficient, okay? Because you do not have now extra these contacts. Okay? So this is one extra contact, and this is the
Can
second.
you please explain style number 2 once again?
Number two, this one.
Yes, sir, this one.
So the style number two, that is this one. I mean, these two are the way of drawing the layouts. Any designer would, can draw the layout in a different manner. But yes, there has to be some common practice, some common rule, common laws by which the layouts can be created, and that layout has to be efficient. That is, the layout area should be minimum. Okay. So if somebody is not following some rules or some method, then maybe people will end up in such design, right? This design, or maybe this design is also created without considering any rules. Okay, so that is why the placement of transistors is different here. Okay, we don't know that this placement is optimum or not. Can you please turn off your mics? So we don't know whether these placements are optimum or not yet. Okay, because we have just arbitrarily drawn everything. So for example, here in this case, second one, this one. So here you will see that the diffusion region is breaking over here. That is the NMOS. This is NMOS B, transistor number B for NMOS. So this is having a different diffusion region. Okay. But here, if you consider in this case, first case, you will find that the diffusion region here is same, right? That is A, B, and C. All are sharing the same diffusion region. Right? This green line is the diffusion region for NMOS. So they all are sharing the same diffusion region. Here they are not sharing. That is, B is sharing a different. A and C are sharing the diffusion region, but B is having a separate diffusion region. So because of that, you have extra contacts also in the diffusion region now. So this is not an optimum.
Why we need different diffusion region in second case?
Yeah, because designer is illiterate, so that is why it is different. So designer is illiterate, he doesn't know how to draw the layout. So one has to train the designer, so one has to make him learn the methods of drawing the layout. So that method actually we are going to learn now. Okay.
Sir, one more question. Hello, sir.
Please.
Sir, we can draw in a one diffusion layer if we take a C in between. C
Yeah.
ट्रांजिस्टर
Oh,
अगर
so
हम C
see
ट्रांजिस्टर
here.
को बीच में डालना चाहें उसके बाद भी हम एक उसमें कर सकते हैं.
Okay, so that is again arbit. So you're not following any method, you are arbitrarily drawing. So maybe also you can bring in between and say that this is the best or optimum layout. So it may not be optimum, but yes, in these two it looks like that this is more optimum because it has lesser wirings also, and the diffusion regions are also shared, so contact resistances are also small. So point here to make is that this one is more optimum, it looks more optimum, though it is again drawn arbitrarily without following any method, and this one is also drawn arbitrarily. So the point here is that we must adhere to some common method by which one can draw efficient layout where the placement of these transistors, so that also has to be also given to us by some method which can say that okay, this placement of transistor would be more efficient. Okay, so that kind of method we have to learn. Okay, these two are all arbitrarily drawn, right? So both are not optimum, but yes, this looks more optimum than this, as I said, because the diffusion regions are being shared here in this one, number one, and the contact resistance for the diffusion region is small here. Okay, so we have to learn better algorithm, some sort of method. So that method is Euler's method. So that let us learn that method. Okay.
Excuse me, sir.
Yeah, please.
Sir, how to identify the source and drain?
How to identify
source and drain regions?
Yeah, source and drain regions. So source, for example, here, source of MOSFET is PMOS is connected to always the VDD, and similarly for source of NMOS that has to be connected to the ground. Okay, so one can identify source and drains. So source is this one, then this is drain, then this is source, and the current direction is also important in deciding source and drain. So similarly, this is drain to source current for NMOS. Okay, so drain, source, and similarly this one would be drain and this one would be drain for this. So that way one can identify source and drain.
Sir, in layout, sir.
Yeah, layout you have
in
to.
the stick diagram, sir.
Yeah, so in the layout you have to see which node is connected to which node. So for example here in C, MOSFET number C here, yeah, C. So source of C is connected to the no, sorry, this is drain and this is source and this is drain. Sorry, these two are drains and these two are sources. Okay. So for example, in these three MOSFETs, CAB, source of C here, that is at this point, source of C is connected to drains of A and B. Okay. So source of C is connected to drains of A and B. So let us see here, source of C is connected to drains of A and B. So this is maybe one can say that, yeah, so source of C is connected to drains of A and B. So this may be the drain of B and this may be source of C. Okay. And this is drain of A and this is source of A. Similarly, this is source of this and this is drain of C. So that way you have to identify. Again, you have to refer to circuit for identifying drains and source in the layout, from the layout. Right?
Sir, in that case, we have same diagram for the two different circuits.
These two circuits?
No, sir. For the second case only,
Okay.
the stick diagram is same for two different circuits.
Stick diagram? This one?
No, sir, that layout one.
Okay, layout. This one?
Yes, sir. Second one.
Second one. This one second. This one?
No, sir. This one first one only.
First one. First one?
First one is for two different circuits. It is same.
two
Because
different.
because we are assuming drain and source based on the circuit only, but the layout is fixed.
Yeah, so in the layout, you will have to define your source and drain also. So, you know, the source, as I said, that here the source of C is connected to the drain of A and B, right? So source of C is connected to drain of A and B. So I say that this is my source of C, okay, and this is my drain of B. So both are connected here. Can you see here? Oh, where is it? Here, this one. So is it source is connected to drain of B? Okay. Source of C is connected to drain of B. So that is what is this connection. So are you okay with this now?
Yes, sir.
So similarly, you will identify the drain of A now, and then drain of A will be connected to this point. That is,
Sir, in this first stick diagram, sir, the position of drain and source by, sir, we can assume by own. Sir, in the A, you can take drain on the left side and source on the right side. But in the B, you take source on the right side and drain on the left. Source on the left side and drain on the right side.
so that you have to decide wisely, okay, depending on the layout, checking the layout connection and then deciding which will be source and which will be drain. So there is no method for that. You will have to take decision wisely using your own brain, looking at the circuit.
So we can take any side drain, any side source.
Any side drain, any side could be source. So depending upon the circuit connection, you have to decide. Okay. So there is no method for that case. So you'll have to wisely decide by looking at the circuit. Okay. So now let us come on to this technique, that is how to draw the layout by using Euler method, right? So this is Euler method for layout design. So if you follow this method, then the layout can be efficient. That is, it can consume smaller area, and the transistor cells can be also placed optimally, right? So everything will be optimum if you try to draw your layout using the Euler method, right? So let us try to implement or draw the layout of this function. Okay? So let us say this is my function AB plus E plus CD whole bar, right? So since it's always complementary, so I'll use complement here. Okay. So the circuit can be designed this way. This is AB, and this is plus E plus CD. Okay. Now the dual of this would be in the PMOS. So that way my circuit can be designed. Now after designing the circuit, one has to create a graph of this kind, right? So this graph again represents the same circuit. Only thing is notice is that this time we have nodes also here, so you will mark the nodes in the circuit. For example, this is node number VDD 1, 2, okay, node number output, out node, then 3, 4, and VSS node. So between each node you have a transistor, obviously. So you don't draw a transistor here, but you draw a curved line like this, so which represents the transistor. Now for example, this edge and this edge, so these two represent a transistor now between node number VDD and 1, right? So between VDD and 1 we have transistor number A and B. So node number VDD and 1 we have A and B. Similarly, between 1 and 2 we have E, transistor number E. Similarly, between 2 and output we have D and C, and between output and VSS we have A and B in series, and then between output and VSS we have E also, and then between output and VSS we have D and C also, right, from this circuit, right? So we have to draw this kind of graph. Okay, so this is required. Now the next thing is that we need to traverse all these nodes, okay, in maybe either a clockwise or maybe anti-clockwise, whatever way you want to visit. I mean, one has to visit all these nodes in this graph. So for example, all these nodes, that is VDD 1, 2, output 3, 4, VSS, all these are nodes. So one has to visit all these nodes, and while traversing through each node, one has to visit each edge only once. Okay? That is, this is one edge and this is also another edge. So you are, while moving from node number 1 to, let's say, VDD via this path, okay, so you will only traverse through each edge only once. So one has to cover all the nodes And the condition is that for covering all the nodes, you have to visit each edge only once. Okay? So for example, let us say we start from here, node number 1. Okay, so from node number 1, one can visit node number VDD. Then from VDD again can come back to node number 1. Nodes can be visited twice, thrice, but edges cannot be visited twice, right? So node number 1 to VDD, then VDD to 1, then 1 to 2, then 2 to output, and then output to again node number 2, right? So that way one can cover all the nodes and also edges. All the edges are covered. Similarly for NMOS, that is pull down network, one can visit each node by starting from, let us say, output. So output to 3, then 3 to VSS, then VSS to output, then output to 4, and then node number 4 to VSS. So this way we have covered all the nodes of the circuit, and also we have fixed ourselves to visiting each edge only once, right? So each edge is traversed only once, and we have covered visiting all the nodes of the circuit, right? Now this visiting, that is the path that we followed, that is from maybe 1 to VDD and then VDD to 1, okay, or then 1 to 2, or maybe let's say that from 1 to D VDD, when we go, we say it's A, then we come to B, then E, right, then D, and then C. So this is called Euler path, okay, so which is being mentioned over here, right? So how did we visited all these nodes? We visited by visiting all these edges, that is transistors, that is A, then B, then E, then D, and C, right? So this is called Euler path, and this path has to be same for both pull up and pull down network, right? So for this network also, pull up network also, and pull down network, so this path has to be same. That is, it has to be always A, B, E, D, C. If it is not A, B, E, D, C, then that means you'll have to rearrange the ordering of the transistors here in this circuit to achieve the same Euler path for both pull up and pull down network. So one has to reorder the circuit, okay, to achieve the same Euler path, right? So for example, in this case, I'm getting the same Euler path, that is A, B, E, D, C. All the nodes can be visited by, first of all, starting from maybe 1. So A, then B, then E, then D, then C. Similarly here, we start from output A, then B, then E, then D, then C. So Euler paths are same for both pull up and pull down network, right? So this is the prime requirement, first requirement, okay? So if the Euler paths are not same for pull up and pull down network, then one has to modify the transistor circuit, okay, that is this CMOS circuit, so that the Euler paths are same. Okay. Now what next? So this Euler path actually gives me the transistor ordering. So the transistor ordering in the layout is decided by the Euler path. Okay. So that is, my transistors will be placed in this order. That is, first A will come, then B will come, then E will come, then D will come, and then C will come. Okay.
Excuse me, sir.
Yeah, please.
Sir, you said that one has to minimize the number of transistors at the output, no, sir?
Yeah, number of transistors have to be minimized at the output, but while drawing the layout, you have to make a compromise between either the speed or the area.
Means here E must come down, no, sir? The transistor D and C should be up and E should come down, no, sir?
Where E will? This E will come down?
No, sir, in PMOS, PMOS.
Yeah, correct. So that is what I said. You have to.
DC should go.
Yeah, correct. E should come down so that the output capacitance can be down. But then the Euler path of pull up and pull down may not be same, and that is why I say that you have to make a compromise between speed and area. So there must be some sort of compromise, okay, between either speed or area. So if you bring this down, so obviously speed will be more, but area may be different, okay, because then the Euler path may not be same. So for making Euler path same so that the layout area can be optimum, one has to reshuffle the positions of the transistors in the circuit. Okay, so the Euler path gives me the ordering of the transistor in my layout. So the job is now very simple for me now. I don't have to decide which transistor will be.
Sir, if we take the transistor E down and change the name, sir, A, B, C, D. So, sir, it can't follow the path A, B, E, D,
No,
C.
that you should not do. I mean, input reordering.
Why, sir?
We should not do that. I mean, you want to bring this E over here and you want to say that that is D now.
Yes,
So
sir.
what is the benefit of it?
So it will follow the same path, na, sir?
Yeah, but
ABEDC.
yeah, correct. But then you'll have to modify this also here, right? So this will also be called something else. So then the entire circuit you'll have to modify. Pull down also you have to modify.
So, sir, my question is this possible or not?
You yourself think whether if it can be named D.
Function
Can
will
it be?
change.
Function will change. Correct. So it is
Okay.
not possible.
Okay. Okay, thank you.
Okay, so we have a order now, that is transistor, order we have now, ABEDC.
Sir,
Please.
so there, if we shuffle CD up and E down, then it will can't proceed further. It will stuck in the one point. Sir.
Yeah, so then you have to also find out the Euler path. So maybe because this circuit, you will see that this circuit is optimized to have same Euler path for pull up and pull down. So that is why this is placed in between. Otherwise, obviously, if speed is important, you have to put this down.
Okay.
Yeah. So we got a Euler path now, ABEDC, and as I said that Euler path for pull up and pull down networks both have to be same. If they are not same, ABEDC, that is Euler path of pull up and pull down, they are not same, you have to modify this circuit. So maybe this is the result. That is, E was appearing here, but now it is appearing in the center because I want same Euler paths for pull up and pull down network, right? So that my layout is optimum. So, the transistor ordering, we got it. So now the things are very simple now. We have to simply draw, NVL and then active for PMOS. I mean, just draw a line for PMOS here. Maybe this region for PMOS you will draw. And then this region for NMOS you draw. And then simply draw, 1, 2, 3, 4, 5 lines. These lines. So these represent the transistor gates in the same order, ABEDC. Okay. Now one has to provide connections. Looking at the circuit, provide connections. Okay. So how do we provide connections? So this is how we provide connections here now. So we can verify these connections also. Okay. So let us start from the output node. So PMOS, D and C. So both are connected to output. Okay. So PMOS, D and C. This is connected to output. Okay. PMOS, D and C is connected to output. Similarly, NMOS, A and D. And NMOS, A, D, E, all are connected to output, right? So NMOS, A, D, E. So D and E are sharing a common region over here, D and E, and A we take from here, this point, right? So NMOS, A, D, E are connected to now output, right? So this connection is established. Now let us move on to PMOS, node number 2. So node number 2 we have to establish. So node number 2, D and C are connected. So D and C, they were already connected to output. So now these two regions of D and C are left. So we connect them together, D and C. So node number 2 is established. So I write 2 also over here, right? So both of these correspond to 2. Similarly, we move up. Node number 1, A, B and E, PMOS, all are connected. A, B and E, PMOS, A, B and E, all are connected. A, B and E. Okay. So A, B and E. So B, that is node number 1. So B and E we take here, this one. Okay. B and E and A from here. Okay. So A, B and E all are connected. So this is node number 1. So I write here also node number 1. Okay. Then we move further up. A and B are connected to VDD. So these two are left. A and B already are sharing a diffusion region. So now this was left, so this is connected to VDD here. This is my VDD. Okay, now let us move down to the pull down network here. We had fixed up to output node. Now let us fix this third node. In third node, A and B are connected. Okay. So A and B are sharing a region over here common. So A and B are already connected. You don't need to make any other connection over here, right? So they are already connected. No need to make an extra contact. Similarly, let us come on to now fourth number. Okay, node number 4, where D and C are connected. So D and C are also already connected. You don't need to make any other contact over here, right? Now let us come to VSS, where B, C and E are connected. Okay, VSS, B, C and E. So this is my VSS. So B and E are already sharing a region connected, and C we take from here. So B, C, and E are also connected. Okay, so that way the layout design process was very simple. Okay, because I knew what would be the correct transistor ordering. So earlier in the previous case where we were drawing a layout of that circuit which had 3 transistors A, B, and C, we did not know what is the transistor order, optimum transistor order. But here through this method, we have found an optimum transistor order, that is where the transistors will be placed. So we know what will be the placement of all these transistors. So we have placed simply, and then the rest of the things were simple. That is, we had to simply connect these nodes of the circuit in the layout. Right? So the layout process is also simple, and also it is efficient layout in comparison to the previous one where we had drawn everything arbitrarily. So this layout consumes the minimum area also, okay, and also minimum wiring also, okay. Routing is also minimum, and by connecting minimum number of wires, we can route all these terminals of the MOSFETs in this circuit. And the layout area is also minimum, because mostly the layout regions, the transistors are mostly sharing the diffusion regions of each other. Okay. So that way one can think of drawing the layout of any logic circuit, not just this one. Okay. So for example, for an exercise, one can consider drawing the layout of this function by again using the same Euler's method. Okay. Now we have assignment 6 also coming. So where you have to draw the layout of a full adder using the Euler method, right? So you will utilize Euler's method, that is Euler's method here you will utilize. Okay, Euler's method. You will utilize Euler's method to draw the layout of a full adder, okay, so that the layout consumes the smallest possible silicon area. And then you have to also calculate this area and use 2 micron technology. So maybe let us fix the date of this also. Assignment. So today is 10th. So maybe 17th or maybe 16th, Monday. Okay. 16th November, you will submit these assignments. Okay. So I think I'll stop here, and maybe if you have any questions, then you can post your questions.
Excuse me, sir.
Yeah, please.
Can you please extend the date of assignment, as we are not yet done with assignment 4 and 5?
Yeah, so you have to speed up, because this month itself the semester will end for you. So you are having 4 classes per week. Normally we used to conduct 3 classes per week, but since the semester started late, and we have to line up our semester similar to what we are following for B.Tech. So B.Tech people, they I think they have also we have conducted mid-sem 2 also for them, right? Because they started little bit earlier. So you also have to, you also have to speed up. Okay, so maybe I'll extend it here, no issues. But yes, you have to speed up. Otherwise, we'll end up doing nothing then. Right? Things will not be feasible then. So maybe let us extend it to 20th Friday, or maybe 21st, or let us say 22 Sunday.
Yes, sir. Okay.
Yes, sir.
Thank you.
So you have to work hard, speed up, otherwise nothing could be completed. Okay. Yeah, so if you have any questions, then maybe you can ask now.
Excuse me, sir.
Yeah, please.
Sir, regarding assignment 4, I have made one error. Like I have not read correctly that we have to calculate gate capacitances, and rather than that, I have calculated the diffusion capacitance using LEdit, and I have submitted. But now, after thinking over assignment 4, I came to a conclusion, and I now know how this gate capacitance is calculated.
So you can submit it again then. And let us discuss about these assignments later. Maybe if you have any queries about the lecture, then maybe we can discuss them first.
Yes, sir.
Yeah, please.
Sir,
Yeah,
excuse
please.
me, sir. Sir,
Please.
I have a question. Sir, can we expect a different Euler path for same circuit?
Yes, it is possible.
So
different
our
Euler paths, but the path for pull up and pull down network should be same. You can expect a different path, no issues, but both the pull up and pull down network path should be same. Then only the transistors will share the same or common diffusion region. Otherwise, then the layout will not be optimal. Yeah, please.
Sir, if you can explain once again how path will be same, which you explain.
Okay, just a second. Just a second. Just a second. Yeah, so here, so if I start from here, node number 1, okay, so A, then B, then E, then D, then C. So other path could be, I start from B, I mean 1, then I go to B, then A, then E, then maybe C and D. So this could also be one path. Okay. Then you have to see whether this path is feasible with NMOS pull down network or not, right? That is going to B, then coming down to A. Yeah, B, A, E, C, D. Right, again, yeah, B, A, E, C, D, right, B, A, E, C, D, again, B, A, E, C, D. So is it possible here? B, A, E, C, D, it is possible. So the other path could be B, A, E, C, D, yeah, because pull up and pull down network both are sharing same path, B, A, E, C, D, A, B, E, D, C also, and B, A, E, C, D. So both are possible. So it can have two different paths, but the main thing is that the path should be same for both pull up and pull down network. Yeah, anything else?
Sir, sir, from which point we are starting, sir? Like in pull-up network, we are starting from VDD.
Any point you can start. Any point you can start.
Okay, sir, we can visit the node more than once.
No, node you can visit more than once, but edge you should not visit more than once.
Okay, sir. Means starting point and ending point should not be same.
Yeah, it doesn't matter.
Cover all the edges.
Yeah, it should cover all the nodes and all the edges. Edges should be covered only once.
And we can start at any place.
At any place.
Sir, we can start at output node.
You can start.
In that case, if E is below, then
but then how, yeah, but then how we will come back? I mean, from here, if I start, then I go to D and then C, then where?
No, sir. Suppose if E is below and DC is above.
Okay, E, then C and then D. Again, gadbad ho gaya na? Again, it's a problem. So you bring E down, then E, then D and C. Again, it's a loop. Right? So you bring E here, E, then D, then there.
B, C.
So A, then you want this. Right? Where we will go then? This is A, B, and this is D, this one is C, and this is E. And you want to start from here. So you go to E, I mean, you traverse from here, E. Yeah, it can be. I mean, you go to E, then C, then D, then A, and B, again D. Then E, D, A, B, C. Right? So that should be present here also. E, D, C, B, A. Oh, here if you go E, then D, then C, then B, A. Right? E, but here E, D, A, B, C, or E, D, C, B, A. E, C, B, A, D. So here it's not possible. Path exists in pull-up network, but not in pull-down network. So both are not same in this case. Is it okay?
Yes, sir.
So you can find it out here, E, D, A, B, C. So this could be one path, other path could be E, C, B, A, D. Okay, so this is for pull-up network. So pull down, is it possible? So E, D, C, no. Then next one here, E, A, B, no. Not possible in pull down. Yeah, anything else? So So if you have anything else, then we can discuss. Otherwise, let us end the meeting.
Sir, excuse me, sir.
Yeah, please.
Sir, means in CMOS inverter, there in PMOS design, AB is close to VDD, no, sir.
What is close to VDD?
AB means AB.
Okay, let me go back to. Oh, it is already there. Let me go back there. This circuit.
Okay, sir. Yes. Sir, here AB is close to VDD.
Okay.
AB both are in parallel.
Okay.
Means here in NMOS, AB both are in series.
You're correct. So that is dual actually.
Okay, sir. Means is there any rule like AB should be close to ground because in PMOS, AB are close to VDD, or we can design in any way, sir?
Yeah, that we have to actually learn in this course. So there are many things that are that have to be covered. Inputs also, reordering of inputs, the patterns of inputs, the positions of the inputs, so all matter. So that we will learn maybe in the next 2-3 lectures.
Okay, sir.
Hello, sir.
Yeah, please, please.
Sir, do we have classes on Friday?
Is there a holiday on Friday?
Sir, next day Diwali.
Yeah, then no class.
Okay, sir. Thank you.